This is challenge system 2 by me. So there was a couple different goals of it. These are the first ones. And then it's going to be, the first one's going to be the scenario as a thermal resistance network. The second one's going to be the heat transfer rate of this problem. And then the third one's going to be the temperature at the different edges and mediums of the different edges / mediums of materials. So this is going to be the modeling of it. The first thing is going to be these resistances. We can just basically make them in series, and just this is the first one. This is going to be the resistance of the plate. This is the resistance of the insulation. This is the resistance of the bar. This is the resistance of the other plate. These two just come together, and you just add it together like that. And these two are separate than these two when we actually have to calculate it. I did that in a separate Excel file. The heat transfer I got from doing this is going to be Q dot in watts. It's going to be 996. Temperatures at the edges of the different mediums / materials. This is T1, this is T2, this is T3, this is T4. We lost about 0.05 degrees Celsius from T1 to T2, and the same thing from T3 to T4. And then in the insulation, we lost 20 degrees, 21.9 degrees to be exact, or around there, 21.889, I think. That is a crazy high amount in between the insulation, so this is the major heat loser in this equation, or this problem. So then goal 2 is just going to be, you can read these if you want, but they're just kind of going to be all explained in the next couple slides. It's just a brief overview of everything I'm going to run through. 3 different examples with 3 different changing parameters from the same problem. And we're going to go through the human body's thermal conductivity. This is something I found online. I thought it was a cool thing to use instead of the insulation that we are normally using. And then we're going to talk about the ways that this can be a perfect system. We can make it a whole heck of a lot better than what it currently is. So the first parameter that I changed was adjusting the insulation bar thickness. And when I was adjusting the insulation bar thickness, I realized quickly that where we currently have it, or a little bit larger or thicker of a insulation, would be the perfect system. If you get any smaller, you're going to lose a crazy amount of heat transfer, and it's just going to be absolutely pointless in what we're doing. And then if you get anything bigger than around 0.2 to 0.3 to 0.4, even if you really are wanting that, like that's 0.5 is about 1.75 feet as a crazy thick insulation. So right in here would be the sweet spot. This is going to be an exponentially decreasing graph. So as we get even bigger, it's really, you're not losing, you're gaining a whole lot. But if you get any smaller, you're getting a crazy difference. So you want to stay somewhere around from here to here, an ideal scenario. The next thing I did was adjusting the insulation K value. I found that it was a exponential decay rate, and as we increase the K, it's just going to be drastically increasing the heat transfer Q dot watt loss. I mean, there's just really no point to be anything higher than what we already are at with the 0.035. If we get smaller, we can save a whole lot of energy. I don't know how much smaller we can really get, and realistically we can get an ideal world, but we can try. So anything up here is just a waste of time and money and just energy in general. Anything down here could be more expensive, but it could honestly be worth it in the end for some people. So then adjusting the steel plate thickness, we got a linear relationship. As the steel plates get bigger, we save a little bit of the heat transfer, but really it's not anywhere near effective. Anything more than what we were already at with a 0.05. Wait. No, we had 0.03, I think, thickness in our problem. 0.02 was our thickness. So if we get out here, it's just really a waste of everything. I mean, the material to get a 3 meter thick steel plate would be ridiculous. So we just honestly just really want to stay right here. If we need to, we can make it a little thicker. If it's in our problem that we're using, it's going to be less than ideal to have a 0.03 meter thick piece of steel. Like if we're trying to have like an insulation on a house or something like that, we need to go thicker to actually protect the house and keep out, like, say, like a ball hitting it. You don't want a ball to tear through the side of your house, so we'd want it a little bit thicker to withstand that. And then the insulation that I decided to change it to was going to be the human body, and these are just the standing posture. The seated was just, if you're standing, you're going to be more, you're going to give off more heat, so it's going to be a little bit lower than if you're seated, or a little bit higher. This was the different values. They're almost 5 times what our original one was. We got 996. So overall, we can deduct from this that we are not a good insulator, and we're going to have a lot of wasted energy if we use the human body as an insulation. This is why we always have to wear, to stay warm, we need like sweatshirts, coats, clothes just in general. We even sleep with blankets because our body is just not a great insulator. So some final conclusions is based on the effects of changing the design parameters in insulation material. A couple ways to redesign it to improve it would be adjusting the things that I said. And key, we're going to be wanting to make the bar / insulation thickness decrease, the K value. We're going to need to increase the bar and insulation thickness and then decrease the K value and get a thickness of steel plate that is feasible and strong enough to protect the wall or whatever it is that we're using in that scenario. We're engineers, we can, we know how to do that. So then goal 3, I'm going to be giving some background on the problem of energy insecurity, discuss the qualitatively, analyze the single versus double pane windows, and then finally we're going to be talking about the societal implications of improving insulation and window efficiency and what that can mean for the few humans in general. So first I want to start off with the quote, and then it was going to be from an article I found online. Achieving energy equity entails giving groups different types of tools such that they can equally take advantage of opportunities or reach a desired goal. And then energy insecurity is going to be the condition faced by households when they cannot readily afford or access sufficient energy for living and health-related needs. Addressing energy equity means providing tailored solutions such as subsidies, energy-efficient technologies, and educational programs to ensure all groups can sustainably meet their energy needs and improve their quality of life. And that's just a brief overview of it. And then the energy insecurity encompasses not just the physical aspects of energy systems, but also economic and behavioral factors that can worsen health outcomes, highlighting the need for a comprehensive approach to energy policy. This is just an overall, we need these things. The better they are, the less other people are going to have to worry about them. That's just going to be better for everyone in the world. Better health experiences, other things like that. So then single versus double pane windows. Multi-pane glazing can significantly reduce the heat transfer on windows. This was from an article that I found online. This is basically just saying that if we have specialized double pane windows, we're going to be greatly increasing the amount of money we save, because we're not going to be losing as much heat transfer through our windows as we would in normal situations. That's why if you see like big multi-story towers, they might even have triple pane windows in their buildings they can see through, but it's just a way to keep heat transfer and not have to be heating the outdoors as some people do when you leave the doors open to your house and things like that. So my thesis was going to be improving insulation and window efficiency stands as a critical measure to achieving environmental sustainability, economic savings, and social equity, thus forming an essential component in the transition towards more resilient and equitable societies. So a couple different supporting arguments are going to be environmental sustainability, economic savings, social equity, health and well-being, and then energy security. First one's going to be upgrading insulation and efficient windows can cut down on heating and cooling needs, lowering energy use and greenhouse gas emissions like the less energy that we have to use, the less coal that we have to burn. And if we get it down to a low enough point, then we can really be just not burning anything and using wind or hydroelectric or nuclear or other things like that. Economic savings, I've already mentioned this multiple times. It's just lower energy. It's going to be better for people, cheaper. And then social equity, it's going to be helping the lower income houses that don't have the ability to afford these things. This is going to go back to the economic savings. If we have to pay less, they also have to pay less. It's going to be better for them. They're going to be able to do more things in life. They're not going to be fighting check to check. And health and well-being, I'm pretty sure I also mentioned this earlier, that if we're having better heated, better cooled areas, we're going to be facing less health problems. They're going to be coming to people that are not in favorable situations. And energy security, it's going to be enhanced building energy, reduces reliance on external energy sources, fortifying national energy systems against fluctuations in fuel and supply and prices. And that's just kind of, we're not going to have to be relying on coal from other places. We're not going to have to be relying on gas from other places. We're going to be able to generate that stuff in-house, and it's going to be just better. So some societal implications, this is just another quote that I saw, is the energy and security framework includes physical, economic, and behavioral dimensions that lead to or exacerbate adverse health issues. This is just another way to back that if we have better heat transfer rates and we're not wasting energy just heating the outdoors or cooling the outdoors, we're just going to be having overall better health benefits from this. So my overall, I just think that this was a worthwhile thing, and these are my references. And we can take away a lot from just honestly just closing doors every once in a while. We're just saving so much money. If you were to be building your own house, then these were just some things that you can go by, just having the thick enough insulation so you're not wasting money and burning electricity when we don't need to. My references, these were the 3 different quotes on this page. And this one was going to be the quote that I got, or not the quote, the data values that I got from the human body. Thank you.